I've been participating in a couple of CTFs last week, and I just got so irritated because time after time and time again I forgot important things. So I thought I'd record a video just with the things that I usually forget. So it's not a tutorial towards you who is watching it, it's just a reminder for myself. I have two parts of the screen. It's on a Linux system, and I have a couple of challenges from CTFs here, and here is a Macintosh OS X system, and this is here where I'm recording the screencast. So let's start at the phone. It's from CTF, and this challenge was made by Chloe, and the name of the challenge was Lit Phone. So you can immediately imagine that it's a clue, the name of the challenge. It has something to do with phone, and the name of the file is phone. Alright, but you shouldn't trust the ending. If it's a forensics challenge, never trust the file ending. So file phone.wav. The file program tries to look at the magic bytes at the beginning of the file and try to figure out what it is. So it thinks it's a wave audio, but let's apply binwalk too. Binwalk looks at different offsets, but it didn't find any other file formats at other offsets, so maybe it is a wave file. But just to be sure, let's use strings too. So this is part of the standard wave header, and the thing to do here is just browse through it and see if you see some English text. This is just random data. Random data just looks just like this. So when you see something that isn't random data, it stands out pretty clear for the human brain. Alright, so this seems to be a wave file. So let's see here. If I open this with Audacity, let's see, where is Audacity? Here. And I think I have it in the recent files here. So it sounds a bit familiar. I don't know if you're very young, maybe you haven't heard these tones before, but those of you who were grown up in the 90s have heard these tones. But just to be sure, let's look at the spectrogram. Sometimes at these forensic challenges, when looking at the spectrogram, you can actually, and zooming in, you can actually see text in the spectrogram, sound spectrogram, but not this time. This time there you can see something. It's 13 tones, and each tone has 2 frequencies. And if you Google a bit about tone messages and 2 frequencies for each tone, you will find it's a multi-tone thing, and the most common that has to do with telephones, multi-tone frequency thing, it's a DTMF. So Google a little bit more and you will find out that you can decode DTMF on Linux with the Multimon program. There are surely lots of programs, but Multimon is one of them. So let's see what happens. Here it's decoded. The hint, it says for the challenge, it says 0 should be replaced with underscore. Okay, so if 0 is underscore, it's the underscore here and here, then it's probably one word with 4 letters here, and one word with 2 letters here, and one word with 5 letters here. Okay, so how is it coded? Well, the most common encoding with telephones has to do with DTMF encoding. It's T9. I don't know if you remember it. But it looked like this. The letters 2, 3, 4, 5, 6, 7, 8, 9 has letters to it. 0 and 1 doesn't have any letters. And in the hint it said 0 was underscore. Okay, so underscore, underscore, and there's no ones. So it could be T1. Let's see. 2255. 2255. It says bulk But the hint says it has something to do with phone, and you have multiple multiple alternatives. You can create many words with 4 combinations here. So let's try some. Call. That's something that has to do with telephone. The next combination is 6-3. With 6-3 you can maybe create of or me. Let's see what is proposed. 6-3 me. Okay, let's call me. It seems to have something with telephone. And the last one, 6-2-9-2-3. Maybe. And yeah, this might be the flag. Let's see what it means. So Call Me Maybe is a song, and yeah, that was the flag. So that was a simple forensics challenge. And the thing to remember here, try different things. Try bin walk, try file, try to open it in a wave editor if it's a sound file, look at a spectrogram. And there could also be steganography involved. And then you could try to Google for different steganographic software and see if something brings something up. Another forensics challenge, often it's some kind of disk image, try to mount it, look what's inside, and it might be a deleted file in the file system, try to undelete it if you found some software, look at a file system check, FSCK, if it brings something up. It might be a Git repository, look at Git FSCK, look at if something is broken, if something is deleted, if you can restore something. So usually it's hidden in a way like that. And the next problem, and the one that's most often, that I have a very short memory, that I always forget. When it's an exploitable like this is from a tutorial over the wire, the first level of Narnia. I always forget how to interact with the shell. So let's see. In this Narnia case, it's very easy and very tutorial instructive. So yeah, you get the C code. So what happens here? It's a local variable. It's an integer, 41 hex, and a buffer. So if you have done these challenges before, it's probably a matter of overwriting this buffer, but let's read through it. It's a scanf, and it reads up to 24 characters into buff, but buff had only 20 characters reserved, so we have the opportunity to overwrite 4 characters, and those 4 characters are stored just next to buff. So what happens then? It compares the value with dead beef. Dead beef is not what was said to here, but if we manage to manipulate it to have the value dead beef, then it is very friendly and execute a shell for us. So in a normal case, you might have to inject a shell code that execve /bin/sh. When the program enters a function, in this case main, there is functions before main, even in a C program, that initiates the arguments argc, argv, and environment pointer. And when main is finished, here return, you will jump to whatever address that is stored on the stack. So if you manage to overwrite the address on the stack, you will jump. You will control the address that it will jump to. So that's called controlling the instruction pointer, or in this case, when it's x86, the register is actually called EIP, the extended instruction pointer. And on 64-bit, it's called RIP. So R is the 64-bit registers. Anyway, if you can control the instruction pointer, then yeah, in one way or other, you could probably make it jump to some code that you control, that you have supplied, maybe inside a buffer that you put values into with scanf. And the thing with scanf, you can only put some characters into it. because it will bail out if it gets some special characters, so you have to find the shellcode that doesn't bail out. But in this case it's very simple. We only have to put dead beef into val. So it's a simple overwrite. Well, let's try to do it. So run perl, execute something, print maybe 20 A's to fill up the buffer, and append, let's do something naive first, append dead beef. This will not work because its integers are stored in the little endian format. So if we just input it in the natural way, let's see what this prints out. Yeah, it's 20 A's and then something that looks like binary, and it's actually the integer dead beef translated to characters. It looks like that. So if we put this into this executable, way off. It was wrong. It interpreted this as EFBEADDE. And let's see, but we tried to input dead beef. It's DEADBEEF. So the bytes are backwards. And a simple way in Perl to pack the bytes in the right order, little endian order, is with the function pack. Pack. You can just input an integer here, dead beef hex, and you have to tell it how to pack it. And with Perl, it's the big V, it means little endian. Hey ho, and now it actually has dead beef in that variable. So, but we don't have a shell to interact with, because at the moment that Perl had finished printing this thing, the pipe dies and we lose contact with the shell. So we have to think of something to keep the interactiveness with the shell. There are many ways to do it, but one way to do it, you can FIFOs, but one way to do it is just to output it. Maybe /tmp. Usually you are allowed to write to /tmp. Let's see what's in that. /tmp and the file we wrote. Here it is. It doesn't look the same. Okay, anyway, yeah, because we packed it. The bytes are packed differently now. Alright, so if we cut this and pipe it to the binary, we will lose contact with the shell again. Yeah, and we lose it, we doesn't have it. But cut has a special argument. If you write minus or dash, it takes standard input, and I can write whatever, and it gets up here. So if I cut a file name /tmp followed by a dash, it will first cut the file and then continue with standard in. Wow, and then continue with standard in. Great. So if we just take that and pipe it into the binary, we should be home. Now the value is what expected, dead beef, and I have interactiveness with the shell. I am effective user ID is root, and that in the screencast directory. If I type exit, the shell should exit and program quits. And why was the effective UID root? That because of this S here, it means suid root. So it means suid. Set user ID of the executor to whoever owns the program, and in this case root owns the program. So while executing this and this program spawns a shell, the shell will run as effective user ID root. Alright, that was one thing, and the second one was the easiest exploitation challenge from the cybersecurity awareness CTF. So let's just run it. It helpfully prints address of something, of a buffer, and then waits. Okay, let's give it some input. It prints output and exits. Alright, and while I was playing this CTF, I had a friend in the same team who had access to Hexray's decompiler, It's a lot of functions in this binary, but all these are put there by GCC. When you write a program and compile it with GCC, you always get all these functions. And here starts the main. And the main doesn't do very much. It returns here, starts here, and returns here. And it's pretty similar to the previous one. It has two local variables, but this time the decompiler thought it was an integer, but it's not an integer, because let's see how much space it has reserved. 98 minus 18 hex, which is 80 hex, 128 bytes. The decompiler is not correct here. The correct decompilation would be a char, maybe buff, and parenthesis 128, and this what's it called, array parenthesis. Then this 8-byte floating point number is assigned a value. Set vbuff is not so important, and now it prints the value of v4, the buff. And next it reads with scanf into the buffer, and it doesn't check bounds. You can put how many bytes you want into this buffer, and if we put 128 bytes or more, we will overwrite v5. Oh, but what if we put a lot of A's here? Instead of 64.3333, we will get 41, 41, 41, 41, and whatever that is decoded as a floating point with mantissa. And it will not be correct, because the next line here checks if after the scanf, if v5 still has this value. If it doesn't, it prints nope and exits. But if in some magical way it still has the correct value, it will return. And this is the magic thing. And return will read off the stack, the return address, and if we manage to overwrite the stack, we control this address where it will return to. So this is the magic thing. And this is called a canary, or canary value. So it's like in old times when you had a mine, you put down a canary bird, and if the canary bird died, then it was not safe to go into the mine. So it's the same thing here. v5 gets a canary value, and after this dangerous stuff is performed here, if the canary has died, nope, it's not safe to continue. Just exit the program. But the error here from the program developers is that they have a static canary. So it's always 64.33. And what we can do is just run the program, put in a breakpoint, inspect the stack, and see what this 64.333 translates to. It will translate to 8 bytes. If we manage to overwrite first this 128-byte buffer, and then overwrite with exactly the correct 8 bytes, then we can continue and overwrite the return address. And if we can overwrite the return address, we control the instruction pointer. And then it's basically finished. And what we can do, we can put our own code in these 128 bytes and get our own code to execute. But how do we know where to jump? If it has address space layout randomization, ASLR, this every time we run the program, v4 will have a different address. But the people who wrote this challenge was so friendly that they printed out the address. So even if ASLR is enabled, we will know the address of v4. So we can just run, parse this line and see what it prints, and overwrite the return pointer on the stack with whatever it has printed, and then jump to that address. And when we in this scanf, we put our shellcode in v4. Instead of running from the command prompt, usually in a CTF it runs from a socket somewhere. You can take a local file that reads from standard input, writes to standard output, and you make it communicate through sockets with something called xinetd. So it will run this binary whenever someone connects to port 1337 on my local host here. So let's see. Localhost. Yep, it's active. It prints out the buff, reads something, and returns. Okay, let's print out too much, so I overwrite the canary. Ah, it's so slow. Okay, I think now it's more than 128. Yep, and it prints out nope, because I overwrote the canary. The thing to do here is to write maybe a Python program or something else. This time I wrote a Python program, and I got a lot of help from one other guy in the team, Liquidera from Svehack team, and I basically copied this program from him and modified it. This is the IP, this is my local host, and port 1337 is just constant. I will connect further down. Hexdump is just a debug function. It calls hexlify. I just want to inspect the buffer before I send it, so see if I have made any mistakes. Here is a function that reads until it hits a delimiter character and returns the bytes it has read. So I start to connect to the socket on this IP and port. If you remember, when I ran the program, it printed buff colon 0x and then the address. So I start to read everything, buff colon space, everything up to x, and then stop. And then I read again until a new line. And the thing between the x and the new line is actually the string of the address, and just print it out for debugging purposes. Now comes the trick. In Perl you just wrote pack and v, and in Python you write struct.pack and less than L, it's for little endian, and convert this address string into hexadecimal. And then this addr will contain a string which is packed in the correct way, that when it's decoded as a 4-byte address, it will be, yeah, it will work. Here's some shellcode. It's a string that can also be interpreted as executable code. And here's the canary value. If you debug it, you will see that it's those two 8 bytes, this and this, that are stored on the stack, and pack it into 2 string variables. And here's the working message. But we can just do this first to see that the Python program works. Wait to press enter and then send the message. And if we were successful, start to interact with the socket, and you can do that with something that's called telnetlib. This is also thanks to Liquidera, who told me about this telnetlib. Alright, let's run this precision. Okay, the message is a lot of 41s and a new line. Enter, and it worked. Let's insert one more. We had 127 plus new line. Insert 128, then the new line will overwrite the canary with 1 byte. So it should not work. Nope, it didn't work. Okay, so we are absolutely correct there. We can actually, if we do this, then it halts, waits for me to push enter. If I SSH into this, look at the processes that are going, I can see that precision process here is 2932. Start GDB, and I have to do sudo because it's owned by root. Precision. Come on. Right, password. And attached to this process. So I'm in a kernel syscall, and it's waiting to do something, and it's probably scanf, because we already looked at the source code. Press enter. Woohoo! Finish here. Finish here. Finish here. We're still in libc. Finish here. Still in libc. Finish. Still in libc. Still in libc. And this ISO99 scanf, that was actually called from main. Yeah, and now we're back in main. And to see the disassembly, you can write this as main. You see the full disassembly of main, or you can display. Alright, here. So it does a lot of things with floating point. Yeah, and this is probably the comparison. And if the comparison is wrong, this jump will fail. It will not jump to this address. If you remember in the C code, then it will go here and put the error string nope. So we want it to jump to 164. Let's inspect the stack from the stack pointer. Alright, there's a lot of 41s. And then there's this value and this value. Well, it's not overwritten. Or is it overwritten by 1 byte? Let's see. No, it didn't work. We overwrote it. Anyway, if we look at the stack again. So see, here is the first 4 bytes of the canary, second 4 bytes of the canary, then there's something, 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 and here is the return address of the stack. So, because of alignment, we have to actually put 4, 8, 12 more bytes on the stack, and then we can overwrite the return address. So that was the information we wanted. So if we continue, this will not work. It put nope and ended. So let's just edit this. Instead of just this, we want to add... we can just do the full thing. So it doesn't take forever, this video. Instead of just A's, insert the shell code. And then 128 A's minus the length of the shell code, plus the first canary 4 bytes and the second 4 bytes of the canary value, and then the padding because of the alignment issues, 12, and we can put in B's just to see if we hex dump the stack, and then the address, and the address should be packed, and we did it up here, and a new line. Alright, let's run it. Enter the pawn, and did anything happen? Yeah, we have a shell. Alright. And that was the tricks. If you have a local file, cut, and then the exploit, and then a minus or a dash, pipe the file. And if you're on a socket, send the exploit and then use telnetlib.interact to interact with the shell that has been spawned. Yeah.